So we are discussing periodic classification, and we are at the most important subtopic, that is Lanthanoid contraction and its applications. And I was telling you this because you have n number of properties. I was discussing all this. And remember that the Lanthanoid contraction applications you can bank on, because these questions are supposed to come in exam, whether it's an advanced level JEE or medicine or whatever, you're supposed to get it, right? And also I would like to love to remind you, when you deal with periodic classification, I was always telling you that it's not trivial, it's not silly. You have infinite number of periods, right? You have infinite number of shells in an atom, and each shell is a period. So you can expect infinite number of periods, right? But the seventh period itself is incomplete. When the seventh period is incomplete, it leaves the scope for you to go out, check out for elements, bring them in. I think I have a place in the periodic table for you. So it basically it's not silly, but it actually stimulates research. You must understand that. It stimulates research, and it leaves the scope for you for dealing with any new elements discovered, not only now, from years from now onwards. You must understand the place is fixed in the periodic table. And that's number one, which I would like to always remind you. The second point which I would like to tell you is, you have the modern periodic table which we are discussing, where you have 7 periods and 18 groups. You must understand, you have 18 groups. But at the same time, understand that the basic difference between all the elements in the periodic table is nothing but their sizes. So the mode of activity, or the chemical or the physical properties, or the mode of activity is basically dependent upon atomic radii. You must understand. So even the modern periodic law is framed on the atomic radii, kept in mind, the atomic radii itself. So understand that the physical and chemical properties, or otherwise I call this to be a mode of activity, is basically a function of atomic radii. You must understand. It's basically a function of atomic radii. The second thing is basically, there are certain properties which repeat themselves at regular intervals in the periodic table. And such properties are called periodic properties. And we were discussing several periodic properties, and ultimately we are ending up at, they are also depending upon the atomic radii. So in the first place, we have defined atomic radii, and then we have seen the trends of atomic radii, how does it vary in a period and a group. The second one which we were discussing is electropositivity, which is a periodic property. It's also a function of size. And then we are discussing electronegativity, then you are discussing electron affinity, then we are discussing ionization potential, and one major factor which influences this ionization potential was shielding effect or screening effect. If you recollect, we were telling, if in between the nucleus and the outermost shell, if the number of shells increase, then the nuclear force of attraction that is supposed to fall on the outermost shell basically decreases. Then what happens? The outermost shell goes on in a relaxation mode. When it goes in a relaxation mode, the size will be actually increasing. But if you have in between the nucleus and the outermost shell, suppose if you have bad shielders like the F subshell, where the bulk of the electrons are added, then I think the outermost shell will be pulled inwards, thereby the size decreases. You must understand. So two things keep in mind. Between nucleus and the outermost shell, two things you must keep in mind. Number one, if the number of shells increase, anyway they will increase. On the top, the electrons are present in S, P, D, F, in between these shells, is also important. Because if you look into the trend, S is a better shielder, P is a better, compared to P, compared to D, compared to F. So if the bulk of the electrons are added to F subshell, then I think the shielding effect will be lesser, and the nuclear force of attraction penetrates through the F, and finally falls on the outermost shell, which results in a decrease in sizes. Whereas if the bulk of the electrons are added to S and P, they are good shielders. They are basically good shielders. So thereby the outermost electron is basically in a relaxation mode. You must understand that, right? So these are all the things regarding shielding effect. And one major consequence of this shielding effect, which we see in the form of Lanthanoid contraction, you must understand. We see in the form of Lanthanoid contraction, and we are getting and dealing with applications. And I would like to remind the students that all the applications which I'm writing here right, will be questions in exam at the advanced level or even any exam which you are going to write, right? And let me brief what exactly is this. Remember lanthanides. Remember, I draw the attention of everyone, please. Lanthanides belong to sixth period. They belong to sixth period in the periodic table. Now, when you are belonging to the sixth period in the periodic table, then what is happening is you are actually far away from the nucleus. From the first shell, second shell, third shell, fourth shell, and fifth shell, and now you are to the sixth shell. When you are to the sixth shell, we were told earlier that when you move away far from the nucleus, the energy difference between the subshells basically decrease, and you must understand energy between the shells decreases, and when the energy between the shells decreases, you can expect the energy difference between the subshells also decreasing. Now, what will happen in such a scenario, since you are actually far away from the nucleus, lanthanides are far away from the nucleus, and you belong to the sixth period, then the energy difference between the subshells within the configurations of the lanthanides also decrease. You must understand that. So what I mean overall is when you get far away from the nucleus, you can expect discrepancies. While writing the electronic configurations based on what? Aufbau's principle, you must understand that, right? So such a discrepancy is one of the biggest discrepancies what we notice is lanthanide contraction. So what is happening here? Remember few things before I go to the applications. Lanthanides are basically 4F series. They belong to what? The 4F series or the F block. And they all start from cerium to lutetium. It is 58 to 71. They all start from what? Cerium to lutetium. That is the 4F subshell, you must understand. Cerium to what? Lutetium. And you have lanthanum also here, which is 57, but it has no electrons in the F. It is having 0 electrons in the F subshell. So I don't consider lanthanum technically, theoretically, based on the properties it can, but theoretically I don't consider lanthanum to be F block. It belongs to D block. But I think this is what are called lanthanides. These are the lanthanides. And look into its electronic configuration. Look into their electronic configurations. The general configuration will be involving 3 subshells, ultimate shell 1 to 2, n-1d 0 or 1, and n-2f 1 to 14. That is the general configuration. So basically you can see here the general configuration of from cerium to lutetium will be, you have 3 subshells. This is called ultimate, penultimate, and anti-penultimate. And if you look into all the 3 subshells, the bulk of the electrons are added to the F subshell. You can actually see 1 to 14. You hardly have any electrons in D. Remember that, right? And also one more thing you must understand, since you are far away from the nucleus, you are almost to the 6th shell, the energy difference between these subshells is almost what? Very, very less. So if you stick to your Aufbau principle and try to write the electronic configurations, you will find discrepancies everywhere in F block. You must understand, right? But anyway, these are the lanthanides which belong to what? 4F series. And what is contraction? What is lanthanide contraction? What we observe is basically this, that when you move from cerium to what? Lutetium. There is a decrease of size of around 0.2 angstroms on an average. This is the size decrease noticed. The size decreases around 0.2 angstroms on an average when you move from lanthanum to what? The lutetium. Right, lanthanum to what? Lutetium. You must understand the size decrease is around 0.2 angstrom units. And 0.2 angstrom units decrease is something which we can't discount it. And it has a bearing on several applications, whether it is physical or chemical, properties of these rare earth elements, that is nothing but what? Lanthanides. You must understand. You cannot discount that. So, few things in an order. Lanthanides belong to 6th period, right? 6th period. Lanthanum is a D block element technically, right? D block element. The elements that follow lanthanum are called what? Lanthanides. You must understand. In all the lanthanides, the bulk of the electrons are added to this F subshell. The bulk of the electrons are added toward the F subshell. So when you are adding that to the F subshell, and F has a very peculiar diffused shapes, right? The nuclear force of attraction penetrates through the F and falls on the ultimate shell, resulting in a contraction which cannot be discounted because the average decrease is around 0.2 angstrom units, so which cannot be discounted at any cost because it has the bearing on physical and chemical properties which we would like to discuss. So if someone is asking you what is lanthanide contraction, you tell him that the lanthanides belong to 6th period. They are removed from the main frame of the periodic table, put at the bottom, and the F subshell is being filled from left to right. So left to right. So whenever you're moving from 58 to 59, the nuclear size is increasing, right? When the nuclear size increases, the nuclear force of attraction also increases. But since the electron is added to the F subshell, it is a bad shielder. The increased nuclear force of attraction penetrates through this F and falls on the ultimate shell. So thereby the ultimate shell, whenever you take one step ahead, in the lanthanides, 58, 59, 60, 61, 62, when you do that, the nuclear size is increasing, the nuclear force of attraction is increasing, and thereby it's penetrating through the F and falling on the ultimate shell. When it falls on the ultimate shell, the outermost shell is actually pulling inwards, thereby you find a contraction in the sizes, and that contraction is referred to be a lanthanide contraction, and on an average it is around 0.2 angstrom units. Now let us check exact values of how the contraction is. Observe carefully. I'll put some values for you. Watch carefully here. This is basically the decrease. See, look into this. This is the 6th period. This is the 6th period, right? And here is lanthanum. Here is lanthanum, whose atomic number is 57, right? And in the 6th period, next element will be 72. Mind you, this is 57 and then 72. So the missing elements, they also belong to the 6th period, but they are put at the bottom. That is nothing but lanthanides. So it is cerium to lutetium, that is 58 to 71. Here the F will be filled. F is what? Filled. After 71, you climb to what? 72. So basically, these missing elements also belong to the 6th period, but they are filled at the bottom. Once they are filled, they go to the top, right? And when you are actually filling the F orbitals, we find some contraction, right? That contraction is called what? Lanthanide contraction. So what I will do, look into this. If you look into the lanthanum atomic radii, which is around 103 picometers. Picometers is 10 power minus 12 meters. Please understand that. The size of lanthanum, the atomic radii of lanthanum is 103, right? So it is lanthanum is 103. And if you go to lutetium, you can actually see the lutetium drops to 86 picometers. So it's basically a drop from 103 picometers to 86 picometers, which is significant, contraction, you must understand here. It's a very significant word. Contraction, you must understand. It's a great word, contraction, which you cannot discount it. understand that, right? So what is happening here is there is a contraction from 103 to what? 86. So when the size decreases, it has a direct bearing on density. And when it has a direct bearing on density, melting points in chemistry are functions of density. So when you have this significant contraction, if you have this significant contraction, you must understand, right? Significant contraction, then you must understand that you will have the density being higher and melting points also will be what? Higher, because when the size is decreasing, the density will increase significantly and thereby it has a bearing on what? Melting point, because melting points are functions of what? Density. And if you wanted to know how these vary, then observe carefully one by one. I'm writing it for you. Watch carefully here. If I look into the effects. Look into the effects of lanthanoid contraction. The first thing is, first of all, lanthanum. The size, if you see the lanthanum size, it is 103 picometers to lutetium, which is 86 picometers. You must understand. You can see a significant contraction. And remember, when size decreases, when size contracts, then density will increase. You must understand. The size contracts, I think the density will increase because density is mass by volume. The mass by volume. And remember, when density is mass by volume, it's mass by volume. And remember, when you move from lanthanum, I draw the attention of everyone, please. I draw the attention of everyone. From lanthanum to lutetium, there is a significant increase in mass because you're starting from 58 atomic number, 59, 60, 61, 62, atomic number is increasing. So you can expect atomic weights also increasing very, very significantly. Extremely significantly, they will be increasing, right? So there is a mass increase, but the volume increase is not in proportion to the mass increase. The mass is increasing, but the volume is not increasing in proportion toward the mass increase. In fact, the volume is actually decreasing because of the lanthanoid contraction. So what is happening? The mass is basically increasing and this is not increasing, so this is basically decreasing. So you expect density will also what? Increase, you must understand. And if I can write the density trend for you, the lanthanum density in grams per what? Centimeter cube is 6.1 gram per volume. Centimeter cube, lanthanum. That is what is the density of this. And it significantly increases and goes on till lutetium. It will be 9.8 grams per centimeter cube, telling us that yes, lanthanoid contraction is a reality and not a story or a fiction which happens. You must understand that. Right? Look into the contraction, direct bearings on what? Density. You must understand here. The density, the lanthanum size is decreased from 103 to 86. The mass is increasing, but the volume is not increasing, rather it's decreasing. So mass by volume is density, then you can expect significant increase in what? Density, and you can see the values increasing from 6.1 grams per centimeter cube. Centimeter cube is the volume, right? And from 6.1 to 9.1 grams per centimeter cube. And also remember in chemistry, like hardness of a substance is a function of density. The hardness of a substance is basically what? Function of density. So you can expect the hardness increasing from lanthanum to what? Lutetium. You should understand that. Right? If I can write the hardness trend for you, the hardness, this is also directly proportional to density. Hardness is a function of what? Density. The hardest substance is what? Diamond. That's because of that. Because why it is hard? Because its density is too high, right? So when density is increasing in lanthanides from left to right, I think the hardness also must increase. You must understand. So hardness directly proportional to density. So from lanthanum to lutetium, basically hardness increases. Now, when someone is asking you, when someone is asking you which of the following is true, is lutetium hard or lanthanum hard? Right? Which of the following is true? Lutetium is much harder than lanthanum. Lanthanum is much harder than lutetium. Both are correct. Sometimes it is hard, sometimes soft, sometimes such questions are asked. It is an advanced level question. You must understand. If you can only write this when you know the subject point, that is lanthanoid contraction. And remember that hardness is a function of density, and density is increasing from lanthanum toward lutetium. So naturally the hardness also increases. So you can expect this question. So I can simply say lutetium is harder than lanthanum. You must understand, right? Lutetium is harder than lanthanum. So look into the trends. This is the size trend which I am writing. This is the density trend I am writing. Density is increasing. Hardness also increases. Now coming to the melting points. Now basically understand that melting points of substances are basically determined as a function of density. In chemistry, melting points depend on density. So if someone is asking you why the melting point of such a substance is more, you have only one answer for that. That's nothing but what? Density. That's nothing but density. So melting points in chemistry, not only here, they are always a function of what? Density and molecular weight or atomic weight. You must understand that, right? So primarily it's a function of what? Density. Once you know the density trend, I think you can expect the melting point trend. If the density is increasing, I think the melting point also will increase. So for the subject point, if you wanted to write down, then understand that melting points are basically functions of density. In fact, more is the melting point, more is the density, more shall be what? The melting point, you must understand. As we have a trend here, the density is increasing from lanthanum to what? Lutetium. You can see 6.1 to almost 10 gram per centimeter cube. You can expect the melting points also increasing in the same fashion. Now, if that is the case, then look into this melting points. Then I can simply say that, if I say melting point increases from lanthanum to lutetium, and approximate values, if you actually wanted to see, lanthanum melting point is somewhat 1193 Kelvin, right? And you end up at lutetium melting point somewhere around 1925 Kelvin. Come on, it's 1193 and 1925. So you have a 1,000-fold, 1,000 units increase in case of what? Lutetium. That's because the density is also increasing in that proportion. You can see here the lanthanum has 1193, that is approximately 1200 Kelvin, and the lutetium is actually melting at 2000 Kelvin. You must understand, these are metals. So you can expect the melting points to be on the higher side, you must understand. But there is a significant increase in melting points from left to right, so indicating that lanthanoid contraction is no silly thing, it is a serious thing, right? And it happens, it's no fiction, and it has a great bearing on what? Properties. And look into the properties once again. The size is basically decreasing, density will increase, hardness will increase, melting point will also what? Increase. So if we can put it at one point, then I would like to say these things must be remembered. These things must be remembered for students who are writing their exams. So remember the trends in lanthanides from left to right. You can actually say from lanthanum to what? Lutetium. You can actually write down, rather, these are the trends. The size decreases, right? Density increases, hardness increases, melting points increase. So when the size is decreasing, the density is increasing, the hardness is increasing, the melting points are also increasing, and I gave you the values of it, right? And there are several other direct consequences which we will be discussing one by one, and the next one is also extremely important, and I draw the attention of everyone, please. The second application of Lanthanoid contraction. The second application of Lanthanoid contraction, if you actually see, this is, you can bank on, this is 100% sure in exam, this is 100% sure in exam, and what is that? What is that? Zirconium and hafnium have similar radii. Zirconium and hafnium have what? Similar radii, you must understand. Zirconium and hafnium both will be having similar radii. Now, first of all, let us plot this zirconium and hafnium such that we can understand where their position in the periodic table, and then we can say and link it to what? Lanthanoid contraction. So what is zirconium? Where is hafnium? Let us understand this, right? So let us have an idea of where to spot these two fellows in the periodic table. Mind you, this is the sixth period. This is the sixth period in the periodic table, and here is lanthanum with atomic number 57. It's 57. And at the bottom, you have 58 to 71, where the F, these are the lanthanides which are placed at the bottom. After filling 58 to 71, these size contracts. These are the lanthanides. They also belong toward the sixth period itself. The lanthanides also belong toward the sixth period itself. But after lanthanum, instead of entering D, they enter F. So D and F is a mix-up in the sixth period. So they have removed that and placed at the bottom of the periodic table. So when you're putting at the bottom, the size is contracting, and the F14, after filling F1, F2, F3, F4, F5, F6, F7, F14, you climb up. So if you actually see the sixth period, in the printed periodic table, after 57, you expect 72. The immediate element is what? 72. This is basically 72. 57, you are supposed to have 58, 59, but it won't have. The periodic table will be having, after 57, you get what? 72. And where are the missing elements? They are placed at the bottom, and those are called lanthanides, where the size is contracting. And this 72 is hafnium. This 72 is basically what? Hafnium, you must understand, right? That is hafnium. So it's hafnium belonging toward the sixth period. And in the fifth period, the corresponding element is zirconium. Remember that. So this is the fifth period, and this is the sixth period. You must understand here. So this is these two are corresponding elements. With this is fifth period. This is what? Sixth period. You must understand. So to maintain the decorum, they have placed like this. Now what is the decorum? Watch. What is the decorum? In sixth period, you have lanthanum, which is 57. After 57, you will notice that there is an element 72. So total of 14 elements which are missing, which are removed from this main frame and put at the bottom. Here the F is being filled, and thereby the size contracts, and then climbs up. Climbs up at 72. That element is what? Hafnium. And this element is what? Zirconium, which is just above that in the fifth period. You must understand. Now what is happening? Since they are actually technically speaking, these 14 elements are also supposed to be here, right? and the size must be contracting, and then the hafnium size, actually between lanthanum and hafnium you have 14 elements. So you can expect a great jump in radii between the lanthanum and the hafnium. Use common sense. If I technically for a moment place these elements here, right? So between lanthanum and hafnium you have 14 elements. So if you have 14 elements, the size must be increasing heavily, very, very heavily. But actually, since you have lanthanoid contraction, the size between the lanthanum and hafnium would not increase significantly because there is rather a contraction which is lanthanoid contraction, you must understand. And the effect is having immediately a bearing on zirconium. Since hafnium size did not increase, the corresponding element in the fifth element is also having the same size. You can actually expect the difference in sizes between zirconium and lanthanum to be too high. Very high. But that highness is actually not seen because technically if you place these 14 elements here, hafnium would have been got the biggest size. But since you have contraction in the 14 elements, the hafnium size and the corresponding fifth period size have similar radii. And I'm warning you, this question is a 100% sure question in the exam. Which of the following is a direct consequence of lanthanoid contraction? Which of the following is a direct consequence of lanthanoid contraction? That's nothing but zirconium and hafnium having similar radii. And if you want the values, then you must understand the zirconium, if you look into the zirconium radii in picometers, it is 155 picometers. And look into hafnium, it is 159 picometers. Well, they are almost similar except for some 4 points. Well, I call it similar because if lanthanum, if it in between lanthanum and hafnium, if you have 14 elements technically, we can expect a huge increase in size. But it is not happening because the F elements you have contraction. And after filling F, you are climbing to the top, that is nothing but hafnium. You can see the radius, it is 155 picometers here and 159 picometers over here. You must understand. Even if you take the ionic radii, zirconium common oxidation state is +4 and hafnium common oxidation state is also +4. And if you wanted to compare this is 83 picometers and this is 84 picometers. And the ratio is basically 1. You can see similar sizes. And it is so surprising to me. It is very surprising to me. For the simple reason, why it is surprising, because if you go home, check the periodic table, after 57, you have an element 72. We are expecting 58. You don't find that. It is 72. That means there is a 14 element missing. So if you have an element 57 and 14 elements in between, you expect the 72 element to be having this much size. But actually what happened, these 14 elements, within the 14 elements you have contraction called lanthanoid contraction. Instead of increase, there is actually a decrease. And when you climb up, between lanthanum and hafnium, you don't have a significant change in what? The radii. So then what is happening? The corresponding element in the fifth element and the corresponding element in the sixth period, both are having similar radii. So you can see the values 155 and 159, nothing to pick between them. And atomic radius of these two is also 83 and 84. The ratio is equal to what? 1. So this is the direct consequence of what? Lanthanoid contraction. So what I'm telling is, understand clearly, first of all, with the direct application of lanthanoid contraction, where you will be getting questions is this. Whether it's an advanced level exam or any other exam, you must understand you get a question on lanthanoid contraction. And more important is this question where the direct consequence of lanthanoid contraction is zirconium and hafnium will have similar radii. Now, first of all, when we say this statement, you must be spotting where is zirconium, where is hafnium. You must understand. Where are those in the periodic table? Well, here is an explanation which I'm giving once more. Look into this. This is the 6th period. Lanthanum is 57, right? After 57, you are expecting 58, but those are placed at the bottom. That's why you find a jump between 57 and 72 printed in the periodic table, and the 14 missing elements are placed at the bottom. Now, what I wanted to tell you is, between lanthanum and hafnium, if you have 14 elements, right, you expect a huge jump in radius between lanthanum and hafnium. But that doesn't happen because the 14 elements have contracted among themselves and then climbing up to 72. So you don't expect a great jump in what sizes, and that will have an effect on an element which is corresponding to the 5th period. You must understand. So the corresponding element is zirconium, which is in the 5th period, hafnium in the 6th period. Both will have similar radii. You must understand. And here is a proof for that. Zirconium radii is 155, hafnium radii is 159. If you look into their ionic radii, that gives a much better information. It is 83 picometers and 84 picometers. Very strange and surprising to me, even at this level. You must understand, it is surprising, right? So that is one case. Now also remember, you know, when the sizes are almost similar like this, like 83 and 84, when the sizes are similar, you know, there is another consequence which will be, which you will be seeing. And this consequence is very natural. And mind you that when the sizes are same, they form homogeneous mixtures. They form homogeneous mixtures like alloys. Alloys are homogeneous mixtures. So basically, what is an alloy? An alloy is one element is an impurity in the other. One element is an impurity in the other. So if you wanted in an element impurities, then the sizes of the impurity and the metal must match. When the sizes match, then they become great friends. For becoming great friends, the sizes must match. You belong to the same classroom. And remember, when the sizes match, then you form a homogeneous mixture. That means that one will be the impurity in the other. Some elements will have only some specific impurities. Why only a particular impurity is present in one element? Why is an impurity, one impurity is an impurity in the other? There is a specific reason for that in chemistry. If the sizes match, then you can live happily and form a homogeneous mixture. Now, if that is the case, this is too much significant here. You watch here, zirconium is 83, hafnium is 84. The sizes are almost similar. And what we will do is we will dig the entire surface of the earth, and we found zirconium. Zirconium is more abundant. And we are looking for hafnium. We are searching for hafnium. I want you to listen to me carefully because this is very significant thing. Since the atomic radius are same, 83 and 84, the sizes are same, zirconium element was abundant. It is abundant. It is everywhere. Then the search for hafnium was continuing. It was continuing. And remember, the hafnium was found 134 years after zirconium was found. Why? Why so many years? Zirconium was readily found. It is more abundant. But the search for hafnium, when they are doing it, they found it 134 years after zirconium was found. That means that the hafnium was, they are actually searching for hafnium individually, somewhere else in the surface of the earth. Right? They are doing it individually as we do it for other metals. But this bloody hafnium is present as an impurity in zirconium. After 134 years of zirconium being found because it is abundant, the individual search for hafnium was continuing as we do it for other elements. We didn't get it. Rather, the hafnium was present as an impurity in zirconium. So basically, when you're trying to purify the zirconium metal, which is tougher, you found hafnium traces in it. So if you go out with a dagger and wanted to dig hafnium, it is ridiculous. Don't do that. Don't do that. In fact, hafnium is present as an impurity in zirconium. And if you ask me why technically, well, I told you that two elements will be impurity to one another when the sizes match. When the sizes match, they form a homogeneous mixture. That's the criteria for you to form a homogeneous mixture. That's why one of the direct consequence of, lanthanoid contraction is zirconium and hafnium having similar radii. The second thing is, hafnium is present as an impurity in zirconium. And it is discovered almost 140 years later of the discovery of what? Zirconium, because it was not present individually, rather it's present as a traces in zirconium. One can be an impurity in the other when the sizes match. And I think, look at these values, this is too much. Zirconium 83 and hafnium 84. Then this is a fit case. This is basically a fit case for one being an impurity in the other. Got my point? So that is one of the application. So zirconium and hafnium having similar radii, zirconium belonging to the 5th period and the hafnium belonging to the corresponding 6th period without any difference in what sizes, and that is because of lanthanoid contraction. You must understand that, right? That is one point. Then coming to the other application, watch carefully here. Solvation energies. Solvation energies, how do they vary in lanthanides? How do they vary in lanthanides? It might be a question in exam, you must understand. This might be a question in in exam for you. Now, first of all, before we actually get into the trend, what is solvation energy? What is basically solvation energy? Well, I would like to define here, first of all. This is the definition of solvation energy. Energy released, and remember, it is always released, never absorbed. So it is always exothermic. It is always energy released. So solvation energy is basically exothermic. It's never endo. It's never endo. So solvation energy is the energy released when solvent molecules surround a particular cation or particular ion rather. It can be a cation or an anion. That can be what? Solvation energy. This is called solvation energy. Is called solvation energy. You must understand. So it's energy released, it's never absorbed. It's never absorbed. It is basically released, it's exothermic reaction. When solvent molecules surround a particular ion, that is anion or cation, that can be called as what? Solvation energy. And assume that if the solvent is water, we call that energy to be hydration energy. We call that to be what? Hydration energy. So if I can show you, observe carefully here. Suppose if it is NaCl, if you drop this in water, right? This is the solvent here. And this solvent will be having a force. This is what I call this to be dielectric constant. That's called a dielectric constant. It is a force which is constant for a particular solvent. And it will be very high for water. It is around 80, 81. So if someone is asking you what is dielectric constant, you tell them that it is force. You tell them that it is what? Force. Now this force is used to separate these two ions. This will be used, this is used, right? And you separate this Na plus and Cl minus separately. How do they separate? Because sodium ion and chloride ions are great lovers. They love each other. It's not easy to separate them. After all, there is an ionic bond. So you must have a great force to separate them. And water has that much capacity to separate these two. That capacity itself is called what? Force. That's nothing but the dielectric constant, which is on the higher side for water. So using that force, it has separated. After separating, right, since they are great lovers, they will look at each other again and recombine. Use common sense. You just can't separate two lovers and leave it off. They will try to recombine because they are charged species. You have positive charge, you have a negative charge. You just can't leave it off, separating them. Right? Then what will happen? The water is polar. Polar means it has charges. This is how water looks like, plus and minus. It has both plus charge and minus charge because you have an electronegativity difference between oxygen and hydrogen. So if someone is asking you, draw water, please draw like this. This is a polar solvent. Right? So the water has separated these two apart, but if you leave them, they will recombine. They are great lovers, bearing charges. So if someone can help in diminishing the charges on them, then they will be stable. That water knows. So water, what it will do, it will surround this ion like this, showing its negative charge. Not one, several water molecules surround it, minus plus, several surround it, minus plus, several water molecules surround it, showing their negative charges towards this positive charge. So then this sodium ion is holding several water molecules onto it. Then we call this to be solvated ion. And since they are actually interacting with the positive charge, the energy released is called solvation energy. You must understand, same will be with the Cl minus ion where the water molecules will be surrounding, and thereby the sodium loses its positive charge. Cl minus also loses its positive charge because water will be showing the positive charge to it. And now the sodium ion and chloride ion are said to be solvated. And mind you that this solvation is exclusively exothermic. And that's what I have written. The energy released when solvent molecules surround a particular ion is called what? Solvation energy. Right? Now the question is, let us come back to this question. What was the question? Solvation energy trend, how does it vary in lanthanides? What we know now, we know what is solvation. Now he is asking us, when you move in lanthanides, that is from lanthanum to lutetium, in which case, from left to right, the solvation energy is increased or they decrease? This is the question. He wanted to know the trend of solvation energies when you move from left to right. That's what he is asking us. For that, let us investigate. Let us please investigate. Remember, I was telling you, when the sodium ion is surrounded by water molecules like this, trying to diminish the positive charge, energy is released, that is solvation energy. Now, student wanted to ask me, when is the solvation energy more? When is the solvation energy more? Right? The energy released will be more when the love is more. When the love is more. And if you want me to show the love, here it is. You can see here the positive charge is loved by the negative charge of the water. Not alone one water molecule, several water molecules are surrounding. And during this love between positive and negative, energy is released. During this love, energy is released. During this love, the energy is released. So the water molecules surrounding, showing their negative charge towards a positive charge, the love is increasing and the energy is what? Liberated. Now if you ask me a straight question, when does the magnitude of solvation energy will increase? Then the common sense is number of water molecules surrounding that sodium if they are more. Number of what? Water molecules surrounding that particular ion, cation or anion, if it is more, then more energy is released. Now the question arises, when does more water molecules surround a particular ion? When does more water molecules surround a particular ion? Is the question. So I would like to write it. Watch carefully. Watch. What are we writing? What is that we wanted? Trend of solvation energies in lanthanides. this trend of what? Solvation energies in lanthanides. That's from lanthanum to lutetium. He wanted to know the trends. Now remember one point. More solvated the ion, more is solvation energy. Remember that. More solvated is the ion, more is the solvation energy. Now what do you mean by more solvated? More solvated means if you take a particular ion, if the number of molecules of the solvent surrounding more, if it is surrounding more, then it is more solvated, right? So the corresponding statement would be more the solvent molecules surrounding an ion, more solvated it is. It is more solvated. You said more solvated the ion, more is solvation energy. Then more the solvent molecules surrounding an ion, more solvated it is. More solvated, and hence more what? And hence more solvation energy. More solvation energy. So more solvated the ion, more is solvation energy. More the solvent molecules surround an ion, more solvated it is, and more what? Solvation energy. Or simply speaking, I can write it like this. It implies solvation energy shall be more if the ionic radius is lesser. You must understand. Solvation energy shall be more if the ionic radius is what? Smaller. So, if this cation, if it is small, then the number of water molecules surrounding it will be more. You must understand. Right? If it is small, it holds more solvent molecules. Then I call this to be more solvated. You must understand. Right? So it's all about solvation energy. Then if this is the case, then understand here, solvation energy is a function of ionic radii. Solvation energy is a function of ionic radii. You must understand. In fact, if you want the relation, solvation energy is inversely related to ionic radii. So the smaller the ionic radii, greater will be the molecule solvated. They are inverse relation. And if this is the case, then in lanthanides, from left to right, that is from lanthanum to what? Lutetium, you have contraction in size. You have basically contraction in size. So solvation energies increase from left to right. You must understand. They actually increase from left to what? Right. You must understand that. Right? So if this is the case, then if you wanted to compare, when you wanted to compare right, the cerium plus 3 versus lutetium plus 3. Let's compare these two. And you drop it in water. Then if this is the case, then cerium plus 3, the number of water molecules surrounding this, right, the number of water molecules surrounding this will be more. So this will be more solvated. More solvated because, no. The size is basically decreasing. So you have a decrease in size. Decrease in size. So you can expect lutetium plus 3 more solvated. It's basically what? More solvated, because there is a decrease in size from cerium to what? Lutetium. Smaller the size, more is what? Solvation energy. So more solvated because you have decrease in size, right? So I can simply say the size of lutetium plus 3 is smaller than cerium plus 3. So thereby it's more solvated. So the energy released in case of lutetium plus 3 would be on the higher side. You must understand that, right? So right, and remember that these are some of the applications of Lanthanoid contraction which I wanted to place them in an order. Watch carefully if I can write all the trends for you. For a quick notes, you can simply say Lanthanoid contraction trends, size decreases, density increases, right? Melting points, they increase, right? Hardness increases, size decreases, density increases, melting point increases, hardness increases. And the other one which I was telling, zirconium plus 4, hafnium plus 4 have similar radii. They have what? Similar radii. This is another trend. And also just now I told you solvation energies, basically solvation energies, they basically increase from lanthanum to what? Lutetium. In what? Lanthanides. You must understand this, right? So remember these trends you are supposed to get in exam. Size decreases, density increases, melting point increases, hardness increases, radii remains same, solvation energy increases. You must understand this, right? That's how it is.